Okay, welcome back. We're going to go over the second PowerPoint for skeletal muscle physiology. First, I want to go over some of the drug interactions. So we talked about, or I had you guys look up drugs, and I want to go over them briefly. I want you to spend some time understanding these and working through these for the exam. You will see some of them in the future in your professional programs. Okay, so let's talk about tetraethylammonium. The first one is tetraethylammonium. What does it do? It blocks potassium voltage gated channels. So those potassium voltage gated channels, if tetraethylammonium blocks them, do they open or do they stay shut? Okay, so if they stay shut, what part of the action potential do they affect? So if you can draw out your action potential, you have depolarization and repolarization, right? Depolarization is dependent on what ion and what voltage gated channel? Sodium. And then what is repolarization dependent on? Good, it's dependent on potassium. And so if tetraethylammonium blocks those potassium voltage gated channels, potassium can't leave using those voltage gated channels. So you stay in depolarization longer, and so it actually hyperexcites the nerves and the skeletal muscles. Can potassium leave the cell though? If it can't go through voltage gated channels, it can. It's going to go through the leak channels, right? So it still can get out of the cell. It's just going to take way longer. All right, so let's go over curare. So curare is going to inhibit, curare is going to inhibit the nicotinic cholinergic receptors. So if you look at this, so here's our neuromuscular junction, right? So curare is actually going to sit on these receptor sites. And if curare is sitting on these receptors, if curare binds to nicotinic cholinergic receptors, what can't bind there? Good, the acetylcholine. So if acetylcholine can't bind to those receptors, are they going to pop open? They're not going to, right? So curare blocks these nicotinic cholinergic receptors. Keep in mind, curare is going to block nicotinic cholinergic receptors from nerve to nerve and nerve to skeletal muscle, because that's where you find them. And so curare is used in some tribes in Africa. It comes from a plant, right? It's a plant toxin. They use it on darts to poison or capture animals. So they'll use the poison arrow or poison dart, and it'll go into the animal's, the deer's system, and the nerve to nerve synapses and the nerve to skeletal muscle synapses will become non-functional. And so the deer will be paralyzed, and that will allow the person to catch up to the deer and then kill it, right? They also used to use this in surgery to hold patients still. So obviously they would have some type of pain blocker, some type of sodium voltage gated blocker for pain, but this would actually paralyze them. Okay, one thing for curare that I want you guys to think about is if curare is sitting on this receptor, so let's go back to the number 4 and 5, I'm in that area. If curare is sitting on this receptor and acetylcholine can't bind to it, is curare reversible, or does it stay stuck to that receptor? Meaning, is it always going to stay on that receptor, or can we wash it out? So if we add more acetylcholine, we can actually kick the curare out. So whatever is in excess is going to bind to this receptor. So it's a lot like enzymes. So if acetylcholine is in excess, it will ultimately kick that curare out. Okay, the next drug is eserine or physostigmine. Eserine or physostigmine is going to inhibit the enzyme that blocks the acetylcholine enzyme. And so acetylcholine can't get broken down, right? So it's going to actually inhibit that enzyme from working. So if you go to the picture again, find your acetylcholine esterase. We'll look at number 7, right? It's in that region. So the blue dots are the enzymes. Those are acetylcholine esterase enzymes. They usually break down acetylcholine. And so these guys are one of the things that help with turning off the impulse. And so if you have serine or physostigmine and it binds to this enzyme so that acetylcholine can't be broken down, what's the outcome? If acetylcholine can't be broken down, it's going to stay in the synapse longer, right? And so this is going to activate the skeletal muscle more. They actually can use serine as an antidote for curare poisoning, or they used to use serine to unparalyze patients. So you put serine, you give serine to a patient, it's going to prevent acetylcholine from getting broken down. And then acetylcholine accumulates, and it's ultimately going to kick curare out of there. So I want you to understand these drugs, you guys. And and understand how they, like what portion of the neuromuscular junction they block. The next one is organophosphates and nerve toxins, like sarin gas. These guys are going to do the same thing. So organophosphates are pesticides, sometimes they're insecticides, right? So the Raid spray has organophosphates in it. It's actually going to block acetylcholine esterase as well. So it's going to activate the nervous system and turn on everything. And eventually the person's going to die because they can't handle constant depolarization of their body cells. For myasthenia gravis is an autoimmune disease. It is an autoimmune disease where your antibodies actually attack your nicotinic cholinergic receptors. So they knock out your nicotinic cholinergic receptors. So if you go back to the picture, let's look at number 5, right? So if you go back to the picture, if you knock out this receptor, and sometimes it's a fast progressing disease, sometimes it's a slow progressing disease, right? So you knock out this receptor, and you have a bunch of other receptors that are still functional, right? But as a disease progresses, it starts knocking out more and more receptors. And so your communication becomes slow and eventually it'll cease. A lot of people have to be put on ventilators because a diaphragm and your breathing muscles don't work anymore because of myasthenia gravis. The antibodies, your own antibodies have attacked your nicotinic cholinergic receptors. One thing that they can give you though is they can give you serine so that the acetylcholine esterase enzymes stop working, so that acetylcholine stays in the synapse longer. So whatever receptors are there, acetylcholine can bind to them. One of the things that they can do with people if they think that they have myasthenia gravis, if they have a droopy face, they can put an ice pack on the eye for a couple of minutes. And the ice pack actually slows down the acetylcholine esterase so that more acetylcholine is in the synapse. And when you pull the ice pack away, the person's eye won't be droopy anymore because there's acetylcholine in the synapse. And so that's one fast way to tell. I'm actually going to see if I can find a video for you guys. So I'm going to stop this. Let me see. And I will see if I can find the video and then I'll come right back. Okay, so here's a video. I just typed in dog's myasthenia gravis test, and it's a positive tensilin test for dogs. So I want to show you, this is a dog who has myasthenia gravis, and they're giving the dog a drug that is similar to serine.
Hey, that's not right. Can we give it to him?
Not yet.
Yeah, okay. Poor guy.
We don't need an MRI.
I heard.
I can make that I mean, over like 5 seconds. That's why she's up.
Where are you?
they see how quickly that drug actually works with dogs, and then they would give this dog, you know, a pill form or you know, an injection on a regular basis. Okay, so let's go back to the lecture. Okay. All right. So again, understand the drugs and how they affect the synapse. Okay, so let's get into a little bit more of skeletal muscle. So we're going to get into a kind of like the whole skeletal muscle, or not so much at the sarcomere level. Okay, so the threshold stimulus, let's cover a little bit of this basic information. So, excuse me, the threshold stimulus is the strength of a stimulus required to cause a twitch. Okay, so we know that for excitable cells, negative 55 millivolts is threshold. There's a certain threshold that you have to meet in order to get a twitch of a muscle cell or muscle fiber. Okay, so we're talking about a muscle fiber. Latent period is a delay between when that nerve zaps that muscle, right? And then you get contraction. So you have to think about all the things that happen during latency period. And this is really important. The nerve gets the muscle excited at the neuromuscular junction. And then that impulse has to be transmitted down those T tubules. You have to release calcium. It has to bind to troponin to move tropomyosin out of the way, for the myosin to bind to actin. And then you actually get contraction. So latency period, it seems like it's pretty easy, but there's a lot of different moving parts. So you need to think about that. Twitch is a single brief contraction of a muscle fiber after a single threshold stimulus. And so a twitch is just one contraction, relaxation of a muscle fiber. And so contraction, we need calcium and ATP, right? And then relaxation, we need the calcium to go away, and we also need another ATP. And so think about how we use calcium and ATP for contraction and relaxation of skeletal muscles. Here is latency period, excuse me. So here is your membrane potential, right? And then your time in milliseconds. And so here is when the stimulus excites the skeletal muscle. And then this is muscle contraction and muscle relaxation. And so think about the stimulus gets the muscle excited, but look at how long this absolute refractory period is. So that absolute refractory period of that nerve or that skeletal muscle is pretty minimal, right? It's about 10 milliseconds. And look at how long that muscle contraction and muscle relaxation takes. It takes about 100 milliseconds, right? And so the absolute refractory period is really minimal compared to skeletal muscle contraction. This is important to know because you know that absolute refractory period prevents a nerve or a muscle from getting stimulated again. So if that muscle is in absolute refractory period for a short amount of time, it means that you can stimulate it really quickly and generate more force. You can get more action potentials and generate more force of contraction. We'll see cardiac in the next lecture, and cardiac is different. Cardiac has a really long absolute refractory period, so you make sure that you can't stimulate it a bunch of times and so that it stays in a contracted state. Okay, so what happens during lag time or latency period? The nerve has to stimulate the muscle, and then the muscle has to produce an action potential, and then you have to actually get contraction. So you need to think about all of what happens during that time period from when the muscle gets excited to when the muscle actually starts contracting. This is latency period or lag time. All or none principle. So at threshold, a fiber will contract to its maximum extent. So if a muscle fiber hits threshold, it is going to contract. It doesn't do a partial contraction. So think of, students tend to think that, okay, well, I am contracting I'm writing or I stop writing, or, I'm lifting something and I pause, that everything stops and it's a partial contraction. And that's not true. So once you hit threshold, your muscle fibers are going to contract. Whatever muscle fibers you stimulated are going to contract. Increasing stimulus strength has no additional effect. And so the nerve can stimulate the muscle, and if it hits threshold, it's going to contract. The fact that the nerve, if you zap the muscle with a stronger stimulus, you're not going to get any more of an action potential, or you're not going to get a higher amplitude from that action potential. A single nerve impulse produces one motor unit contraction, all right? And so a motor unit is the nerve and the muscle fibers that it innervates. How do we generate tension of a single muscle fiber? So how do we generate force, right? Because ultimately we want to generate enough force that we get contraction and we can do work, right? So tension depends on the fiber's resting length at the time of stimulation, how many times you stimulate it, and the number of pivoting cross bridges. Pivoting cross bridges, this means the number of myosin heads engaged with actin. So the optimum length of muscles causes the greatest force of contraction. So if you plot it out, if you take a look at this picture on the left-hand side, notice how the myosin and actin are overlapped completely. Okay, this would be when a muscle is completely contracted. You're not going to contract it any further. When a muscle is primarily contracted, you're not going to get much force generated or be able to do much work. When you have the actin and myosin at an optimal overlap, that's when you're going to generate the most force from that muscle. When the muscle stretched, as in the right-hand side of the graph, you don't have enough actin and myosin overlap to engage it. So this would be like stretching a muscle too far, straining it, or possibly tearing a muscle, right? You can do this example with yourself. You can flex a muscle and try to, like, if you flex your arm and you try to, if you extend your arm and you try to make a fist, that's really easy. It's in the optimum position. If you bend your wrist in towards your midline and contract, it's really hard to do that because of the overlap. If you hyperextend it and try to make a fist, it's really hard because the muscles are stretched out. Skeletal muscles are capable of graded responses. What does that mean? Increasing the frequency of stimulation causes summation, right? And then you can increase the number of motor units activated. So it's recruitment. So you want to think about how much force can you, or how do you increase force? You can zap the muscle more frequently, so it has less time to relax. And then you can activate, the more motor units. And so we call that recruitment. So those are two ways we can get more force from skeletal muscles. Summation, so the third one down, is a greater force generated from more frequent stimuli, and I'll show you that in a second. Titanic contraction is continuous contraction without relaxation of that skeletal muscle between stimuli. All motor units of that muscle are activated. And then fatigue is loss of response due to insufficient ATP. So if we could do this in lab, we would hook up electrodes to your muscle, to your forearm, and we would actually zap it. And granted, your forearm is a whole muscle, and so we would be activating, hundreds of motor units. But this plot shows just one muscle fiber. And so when you stimulate a muscle fiber to threshold, you're going to get contraction and relaxation of that muscle fiber. That's called a muscle twitch, okay? And so this is tension. You can think of tension as like how much force generated. Number two, you zap the muscle fiber, it contracts, and then it starts to relax. And before it fully relaxes, you zap it again. And that is going to cause it to contract again. And before it fully relaxes, you zap it again, and then it contracts again. And so this is called summation, or this is called like the staircase phenomenon. Sometimes you call it trepe. And so notice that we're increasing the number of times we zapped it, the muscle fiber, so that it doesn't have enough time to relax. And so you're generating more force by increasing the frequency, right? This is increasing the frequency more. And so what you end up doing is you end up getting average tension produced or generated from the muscle fiber. And then complete tetany or complete tetanus is when you are stimulating the muscle fiber so quickly with such great frequency that the muscle fiber doesn't have time to relax at all. And so you get this strong contraction. This is tetany. The term tetanus, right, the lockjaw term, comes from the fact that the Clostridium tetani causes your jaw to lock or your muscle to go through tetany. And so that's how they come up with the name. Recruitment. So a muscle is composed of motor units. What the heck is a motor unit? It's a motor nerve plus all the fibers it innervates, right? Number of fibers varies depending on where you're talking about. So 2 fibers in your larynx, 2,000 fibers in your gastrocnemius. Each motor unit responds independently. However, all muscle cells in the motor unit respond maximally or they don't respond at all, right? So let's look at a motor unit. So let's look at the purple cell body in the spinal cord, follow it through, right? And then it synapses with the purple muscle fibers, right? So that's one motor unit. That's the purple motor unit. Then there's a blue motor unit, right? And a red motor unit. Okay, let's say I want to do fine movements like playing the piano or writing. Am I going to recruit one motor unit or all 3? Good. So for fine motor unit, I'm going to recruit one motor unit. What if I want to move a refrigerator, right? Or something really heavy? I'm going to recruit more motor units. Okay. And so that's another way that we can get more force generated. The strength of contraction is determined by the number of motor units stimulated. Recruitment is the process of increasing the number of motor units, right? Or activating those number of motor units. Strength increases as the number of motor units increase. So you can take a look. So the stimuli X stimulates 5 fibers and they produce this force. Then Y stimulates 7 fibers and they produce this force. If you stimulate both X and Y, you generate way more force. And so that's a way more powerful contraction and you can do more work. The size principle, the bigger the motor units, right? Or excuse me, the bigger the fibers are, the skeletal muscle fibers are, the greater the tension is. How do we increase the muscle fibers? If we're talking about, let's say, the biceps brachiae, you can actually weight train, right? You can lift weights and increase the amount of myosin and actin. And so if you have more myosin actin, you're going to have a bigger muscle cell or muscle fiber. You're not going to make more muscle fibers, but you have a bigger one. And so you're going to generate more force. Sustained tension is less than maximal tension. It allows the motor units to rest in rotation so that they don't get fatigued. Think about when you are sitting up and your postural muscles use sustained tension, so the motor units rest in rotation, your latissimus dorsi. Think about when you're carrying like a laundry basket, right? And you're holding it in that one position. In order for your muscles to keep maintaining that position, the motor units are going to rest in rotation. Muscle tone, normal tension and firmness of a muscle at rest. The more muscle tone you have, the greater the metabolic need is for that muscle, even if it's at rest. So if someone is trying to think about losing weight, and they need to lift weights as well as do cardiovascular exercise because they're going to get more muscle mass or they're going to increase their actin and myosin. And because they have that, they're going to increase how much energy they burn even at rest. This shows your tension in your tendon. So here's motor unit 1 turns on, motor unit 2 turns on and shuts off, motor unit 3. And so this is just showing the motor units turning on and off in succession so that you produce a constant tension and that the muscle doesn't get fatigued. Where do we get the ATP for muscle contraction? So obviously we have a lot of mitochondria in the muscles. Sustained muscle contraction uses a lot of ATP. Your muscles actually have enough energy to start skeletal muscle contractions, but they need more ATP. They need to manufacture more ATP. And so muscle fibers, where do they make that ATP, right? You just had an exam on metabolism. So where do they make that ATP? They're going to make that ATP primarily in the electron transport chain. Do you remember what complex uses the oxygen, right? Complex 4. And so they're going to make ATP primarily from mitochondria, from aerobic metabolism. And so skeletal muscles have a lot of mitochondria so that they can make a lot of ATP. Here's a plot. So this shows where you pull ATP from or how we make ATP as we're going through exercise or as we're just going about our daily business, right? So the first few seconds of ATP that you need to get skeletal muscle contraction started is lying around in your cell. Now, don't think that you have a lot of ATP just sitting in your cells, but a skeletal muscle, you're going to have some ATP in that skeletal muscle so that they can start contracting. Okay, then as you're doing seconds of contraction, where do you pull the ATP from? You pull it from this molecule called creatine phosphate. Right, we'll talk about that in a second. As you keep going, though, you're going to kick into anaerobic metabolism. So that is going through what? Do you remember? What's anaerobic? Good, glycolysis, and what do we call the lactic acid production? Anaerobic fermentation. Okay, so we're going to go through anaerobic metabolism because our body hasn't, our cells haven't, they don't have enough oxygen going to them yet. But then as we get warmed up, we shift into aerobic metabolism. And you guys, if you've exercised, which I'm sure, let's rephrase that, as you exercise, you notice that as you're running, for 10 to 15 minutes, there's a point where you start to shift and you feel like, okay, I'm warmed up now. I can handle this. I'm good. Let's push a little faster or a little harder. That's when you're actually warmed up. So you have blood flow going to the muscles. You're making enough ATP for aerobic metabolism and you're officially warmed up and ready to go. Let's back up though and look at the creatine phosphate reaction. So creatine is a phosphate holder. What ends up happening is we have an enzyme in skeletal muscle that takes the phosphate from creatine and sticks it back onto ADP. So let me show you that reaction. So here is, whoops, where's my thingy? Sorry. Here's the creatine, right? And here's our phosphate group, our PO3. It allows us to make fast ATP. So what do we do when we need ATP? When we need fast ATP, we take the phosphate group off of the creatine and stick it onto ADP, okay? So notice how we ripped the phosphate group off of the creatine and we stuck it onto ADP to replenish ATP. And we're left with creatine. The enzyme that does this is called creatine phosphokinase. The creatine then, once we're in recovery mode, the creatine will grab the extra phosphates and reconvert to creatine phosphate or phosphocreatine. So it's ready to go again. So this happens in recovery. This happens when we are, when we need ATP, all right? And it's a really fast reaction. It's one step. And so this allows us to have really fast ATP. Let me back up. So the creatine, what do we do with it if we have excess? This actually gets kicked out of the skeletal muscle as creatinine and we dump it in the urine. Sometimes people who are lifting weights or who are bodybuilders will take excess creatine And this allows them to keep bursting or keep pushing. People think that it helps them recover faster. It doesn't really help your muscles recover faster. It'll help you produce more creatine phosphate so that you can do this reaction again and make more ATP, so you can get more skeletal muscle contractions. So that's true. But when you actually use a skeletal muscle, you do microfiber tears in those skeletal muscles, and they take at least 24 hours to heal. And so that's why when you lift weights, you do your arms for one day, and then you do your legs the next day, and then arms the next day. And so you need to wait for 24 hours for those muscles to sort of heal. So when you lift weights or when you're exercising, or hiking or swimming, whatever, you're doing microfiber tears or microscopic tears in those skeletal muscles. And so satellite cells have to come in there and heal the area. So you have to rebuild myosin, and you're going to build more myosin and actin connections. And so more myosin heads, stronger force generated, right? You're also going to build more blood vessel migration into those tissues so that they become more effective. All right, so muscle contraction and fuel source. So I thought I would put this in here so you can appreciate where you get your fuel from, or where you get your energy from. Now that you've spent some time in metabolism, and we're looking at skeletal muscle contractions. And so for the first 4 seconds, it's anaerobic metabolism. It comes from ATP that's already in the muscles. Then up to 10 seconds, it's ATP in the muscle plus creatine phosphate, right? Then for 45 seconds, it's ATP, creatine phosphate, and glycogen. So you're using up the glycogen to make glucose to go through glycolysis. Then you're going through anaerobic metabolism and lactic acid production, right? And then you start to shift into aerobic. So, 120 seconds, you're starting to shift into aerobic, and then you kick into aerobic once you get warmed up. And so notice how it's aerobic, which is glycogen and lactic acids. You're still doing some anaerobic. And then once you shift into aerobic, you're using glycogen to break down to glucose to make, to go through, glycolysis and Krebs. And you're using fatty acids. So you're always using some fatty acids for fuel. This tells you the number of twitches supported by each energy source alone, and then isometric tetanic contractions. So I thought that was interesting to throw in there now that you spent some time on metabolism and contraction. So take a look at your ATP. That allows you to do 10 twitches, creatine phosphate 70, and then glycogen through anaerobic, just glycolysis, is 670, and then aerobic 12,000 twitches. And so which one obviously is more favorable energetically? To go through aerobic metabolism, right? But we can't do aerobic metabolism right off the bat. We have to get everything sort of going through the whole process and make sure we have enough oxygen to complex 4 to get that electron transport chain going, and that takes a little bit of time to upregulate blood flow, et cetera, et cetera. What happens when our muscles are fatigued? So when they're fatigued, they can't contract very well. This because you usually end up getting a skeletal muscle cramp, right? What happens when our muscles are fatigued? So if we don't have enough ATP, then we can't do muscle contraction. And if we don't have enough ATP, we can't get the myosin to release the actin, and so it stays stuck, and so that can lead to cramping, right? We've damaged that sarcoplasmic reticulum, the sarcolemma, so we have to, and we caused tears to those microfilaments, right? Those myosin heads, actin, and we all have to, that needs to heal. And then low pH, so that area is really acidified due to lactic acid, the protons, and CO2 accumulation. And so we have to handle that as well. We've got to get rid of the lactic acid, and we have to get back to normal pH, right? So a recovery period, what happens? You guys know that when you stop exercising, what happens? You've been huffing and puffing, right? And so what you're doing is you're trying to get more oxygen to those skeletal muscles so that you can make more ATP so that you can contract and that you can recover, right? So you need to deal with the depletion of the metabolic reserves. You need to really build the glycogen stores back in that skeletal muscle, right? You need to repair the sarcolemma and sarcoplasmic reticulum. You need to repair the actin and myosin. And again, that takes about 24 to 48 hours. So you notice after you've done some activity, right? If I go out running, I'm not going to feel sore right away. It's going to take about 24 hours to feel sore. You'll notice sometimes you get swollen because you have more fluid going to that area and everything's trying to heal. And then you have to handle that low pH, okay? So you're gonna process that lactic acid via the Cori cycle. So does the lactic acid stay in the skeletal muscle? No, it does not. Where does it go? It gets dumped into the bloodstream, the liver picks it up, and then processes it back to pyruvic acid and then glucose, and then possibly glycogen to stay in the liver, or the glucose gets dumped into the bloodstream. So the Cori cycle is how we process that lactic acid once it's made. It can't stay in the liver because it's gonna, or excuse me, it can't stay in the skeletal muscle because it's gonna acidify that skeletal muscle. So the Cori cycle is removal and recycling of lactic acid by the liver. And you may think that that is high energy, and it is somewhat, but think about it. This is way better than going out and foraging for glucose or trying to get glycogen from a food source, okay? And then we have to deal with that oxygen debt. So we need to get more oxygen to normalize metabolic activities, right? And so we're gonna huff and puff. And we'll be dealing with huffing and puffing and respirations in a week or so. Heat production and loss. And so active muscles produce heat. About 70% of muscle energy can be lost as heat. So that's raising body temperature. Muscle metabolism. So testosterone, as you guys know, testosterone, growth hormone, and insulin increase muscle anabolism. Is that building up or is that degrading? Good, it's building up. So testosterone and growth hormone and insulin increase muscle building. Cortisol, which is a stress hormone, glucagon, which is what we release when blood sugar is low, your thyroid hormones, and catecholamines. Catecholamines are locally acting hormones and chemicals that excite. So your epi and your norepi would fall under that category, increase muscle breakdown or muscle catabolism. So hormones do regulate muscle as well. Power endurance. So a couple of other things, muscle performance. Power is the amount of tension, the max tension that the muscle can produce. Endurance is how long you can sustain that activity. Power and endurance depends on the types of muscle fibers you have or in physical conditioning. So some of it is genetic, right? So how many fast twitch muscles, how many slow twitch muscles do you have? How many intermediate ones do you have? But then there's a physical conditioning too. If you lift weights and if you work on bursting or if you work on endurance training with running, the muscles are going to respond to a certain extent. Muscle hypertrophy is building muscle. So I want you to think of when you lift weights, people think that you build more muscle cells, and that is not true. You're increasing the number of actin and myosin. So you're increasing the diameter of the muscles, and so the muscle gets bigger because you're adding more actin and myosin. You're not actually increasing more muscle fibers. You're going to increase mitochondria and glycogen reserves in that muscle. The one thing that you'll see with patients or, in nursing facilities or whatnot is muscle atrophy. And so when you have a lack of muscle activity, that muscle atrophies really fast. The older you are, the faster it atrophies. If you've ever broken a limb and had a cast on, you know that that muscle atrophies pretty quickly. I broke my leg. I broke my fibula, and after 2 months my calf ended up looking like my upper arm. It was super skinny, and so it took me a couple of months of physical therapy to get it back to where it used to be. The older you are, the faster it atrophies, and so this is really important because people need to understand that people who are bedbound or in skilled facilities or whatnot, if somebody's laying in a hospital bed for a week and they're 80, they're not going to be able to get up and just walk compared to, a young person. So you need to think about that for rehab, for PT and OT, and what types of activities can we be doing with patients so that they don't atrophy as much while they're in the hospital or in a nursing home or facility. Keep in mind too that what you don't use, you lose. And so the longer a person sits in a bed and refuses to do activity, eventually they're going to lose the muscle, and that muscle is going to atrophy. They also, um, um, fibrous tissue can actually replace the muscle fibers. So if you look at the last one, and this is the most dangerous. And so people who, for example, my father didn't walk for a long time, and he decided that he wanted to walk after, a year. Well, you can't, because you have been stuck in a position for so long that you have fibrous tissue replacing muscle fibers, and those muscle fibers aren't going to respond because they're not there. They're heavily degraded. There is a certain disease, and I can't think of the name right now, but where genetic wise your tendons and ligaments actually ossify over the years. And so I think it's ankylosing spondylitis. And a lot of times people's neck muscles will turn into bone or ossify into bone, and then they won't be able to move their head over the years. It's a really debilitating and obviously leads to an early death. Muscular dystrophy is another big one. So it's a group of more than 30 genetically inherited diseases that cause progressive weakening of all types of muscle. It is due to a mutation. So there's a mutation of dystrophin, it's a protein that's linked to the sarcolemma and cytoskeleton of cardiac and skeletal muscle cells. And so dystrophin is mutated, it's hereditary. And so because of that, the muscle fibers are misshapen. And so if you look at the right-hand side, the top picture is normal muscle fibers. And so you can see some of the white fibers and the red fibers. And then the bottom picture is someone with muscular dystrophy. And you can imagine how misshapen you can see how misshapen these fibers are. And you can imagine how painful it is that those muscle fibers don't contract, they don't respond. People are often stuck in that position, and they have a really low life expectancy. Okay, thank you.